Take a look at
Yeah, let me get set up.
that's bench. The scale for the random walk, it doesn't look like it's really framing anything better. Unless my Monte Carlo is just that good.
That's possible.
Like every run.
Yeah, it's possible if you run it enough.
No, I do have run it a lot. So
Yeah, if you run Monte Carlo enough, it usually converges to the same thing. If there is a true optimum.
well, I did. I closed the figure, but that's what I have to. I'm gonna run it again. It doesn't think that. I currently have it running. Okay. So it's going through and how many times are we doing Monte Carlo? A million? One to the 1 to the 6.
Yeah. Okay. So with a million, it's probably going to get pretty close.
Drop it down.
I mean, you could. I mean, if you want to check and make sure that your second part here, so you're doing random walk.
Yeah.
Okay. So if you want to check and make sure your random walk is doing okay, you can drop that down and make sure that it's still getting to the same thing. But I think right now, because your Monte Carlo is so high, that it's yeah, it's just finding the optimal. I mean, there's just nowhere for it to go, basically. And which is fine, and that's why I mentioned before that if your objective function is just cheap, then there's no reason not to use Monte Carlo because it's going to give you the best thing.
Yeah. And I'm thinking about getting another.
Okay.
Only when the thing I'm getting hung up on right now is forming the what you call it.
Yes, because if you're going to do Nelder-Mead for this one, remember the number of points on the simplex depend on how many design variables you have. So
yeah,
since this one's a four-dimensional optimization, you need 5 points.
Yeah.
So one way that you can generate it, because I do give you the upper and lower bounds for all of these, you can just kind of take somewhat random points between them.
Almost midpoint.
You could do midpoint, so you can do the midpoint between each one. That'll give you 1 point, and then you do like the extreme of 1, and so you can do something like that. It's gonna be a really big simplex actually.
Yeah,
I think you might have some scaling issues with the Nelder. You probably have some scaling issues with the Nelder too, but anyway, okay. Yeah, so the main, okay, so you're scaling each of these as well. Good.
Yeah.
Okay. Okay, so one issue I think you're going to have here is that, and I forgot to mention this to the guys yesterday, but random walk assumes that you're going to be able to walk in the negative direction too, right? Because sometimes the value needs to be lower, and so your H lower and your L H E lower here, these are all positive numbers. So these are the lower bounds for those numbers, right? And so you actually need to make these negative. And so when you're doing random walk, it's a little bit different. So when you're choosing this direction here, it doesn't strictly have to be upper to lower bound here. You can just kind of choose a random number. So that's kind of what I did today. So for L, I believe the L varies between 100 and 500, I think, right?
I don't know.
Scroll down. Okay, yeah, so the length here varies between 100 and 500, right? And so, you know, for the random walk, you can go between like minus 25 and 25, right? And so your L Trouter would be like minus 25 plus rand times 50.
That'd be 25.
Negative 25. Because sometimes you may want to lower the length, right? And you can kind of set these kind of manually based on that. So that's one thing that you'll have to do. But that's different than Monte Carlo. Because Monte Carlo, you're instead just sampling in between the lower and upper bound, and so that has to be set. But for the random walk, you can kind of choose for each one individually. Yeah. Okay, and then you're going to scale it. Good. Okay, so here's the other thing too, is that you don't want to well, I guess you can because you're scaling this, but if you want to be careful to make sure that each one of these is stepping by an appropriate amount too. But if you're scaling the magnitude here, that kind of fixes everything. That's fine. Yeah, besides that, it should do it. And then you're checking all the constraints here.
Yeah, I just kind of took everything from up above.
Perfect. Good.
Yeah.
Yeah. So that's one nice thing about random walk is that you can just straight up reject points, and that's essentially what this does. And it just continues there from on. The rejection doesn't work as well for Neldermead because Neldermead kind of Neldermead kind of has an expectation every iteration that you're actually going to make a step. There's no randomness to it.
Because I put this rank dummy variable in there to keep track of how many times it walks.
Oh, okay.
And that's what I have it where it's right after every day.
This one right here.
Yeah.
This one. Yeah. It could be that it could be that it just never finds a point where it satisfies all the constraints.
Come over here and look at
Yeah.
So that's what I'm trying to. I did drop the other one down.
Yeah.
The other down.
Yeah. So it may. So I think it may before, like, because we did the Monte Carlo so much, it reached a point where it was like so optimum that it just never took a step. That, or it was so optimum, and then whatever step that it took, it just violated it. And so if you took down the Monte Carlo, then you might get some more action. So give that a try with it. And then,
I'll play around with it.
Yeah.
Let's run it.
Okay, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Doing good, hanging in there. It's dark and cold. It's winter now, I guess. Okay, so today,
Next week.
yeah, hopefully.
I don't want it. I keep thinking.
All right, so today is our last ANSYS activity. It's an optional activity, and so I want to emphasize that. So there's nothing for you to turn in. And in fact, there's several parts of the activity at the end. You can do as much or as little as you want because you're not turning it in. But this is really just kind of for your guys's curiosity, because I know that modal analysis is something that is something that's just interesting. It's used a lot for structural design, so it's good to just okay. And this is definitely something you can incorporate into your final project as well. So if that was something you're interested in, definitely pay attention to the activity today, and then you can incorporate it there. Okay. But the idea of the activity today is that we have this gearbox. Okay, so that's a CAD file that I provided to you through Canvas, and we're just going to run a modal analysis on it, and then we're going to see what its natural frequency is. So the activity itself is pretty short. I think I'll probably stop talking maybe about 30 minutes in, and then I'll let you guys just handle the rest of the activity. Or if you want me to go around and kind of check out what you're doing for your final project, you can spend today doing that as well. Okay. All right, and so in terms of the plan for next week, and so remember that I mentioned that the plan for next week is just basically just to use the lectures as extended office hours. Just because I know a lot of you are getting started on your final project, you're kind of grappling with the geometry and the boundary conditions and things like that. And so if you're running into issues with ANSYS with the simulations or anything like that, then we can use next week to kind of help debug those issues. Okay. So if you haven't had a chance to start on your final project yet, or if you don't really know what your geometry is, I would definitely try to do that over the next couple of days, so that next week you can come to the lectures with questions. Okay. Because after next week, the week after that's going to be finals week. I haven't really decided yet on my office hour schedule yet. I'm gonna see just how many people kind of want to meet with me during finals week. But next week's going to be the best opportunity for you to kind of get feedback from me and to help you debug some issues. Okay, so you definitely want to get rolling with that. All right. Any questions on any of this before we get started with the activities today? Okay. All right. So let's go ahead and get started. So because this is an optional activity, I didn't post it on as an assignment on Canvas. And so if you want to have access to the PDF as well as the CAD file, you're gonna have to go to the week 15 page. And so if you go to the Canvas site and you click on this link here for week 15, then the last two files on this page, as soon as it loads, hello, please. Okay, try again. 15. There he is. Okay. And so if you go down to the bottom of the week 15 page, then you'll see the ANSYS 6 PDF, ANSYS Activity 6 PDF, as well as a CAD file called gearbox.agdb. Okay. And so that AGDB file extension is for basically design models. So this is a CAD file that was created within ANSYS. So it should work very well with ANSYS. Okay. All right. So let's go ahead and get started. Oh, question. Yes. Well, I'm not going to grade it or anything. There's no extra credit for it. No. It's mostly just for you to give practice if you want to use it for the final project. Yeah. Okay. So let me go ahead and bring it up here. Files. Sorry about that. I had to pull it up on my iPad. Okay, so let's go ahead and open up ANSYS Workbench here. Okay. Okay. And so first thing we're going to do, before we perform our modal analysis, is we're actually going to perform a static structural analysis first. Okay. Okay. So first thing we're going to do is we're going to start like we normally do. We're going to pull in static structural. Okay. I start with that. You don't have to start with the static structural. It's just kind of convenient to do so because you can take a lot of the boundary conditions and the mesh from static structural and apply that directly to the modal. Okay. All right. So first thing we're gonna do, we're gonna import the geometry. So let's go ahead and right click on geometry here. Let's go ahead and import, and you're gonna browse to wherever you downloaded the gearbox geometry. Okay. You're gonna double click that. Okay, and so the next thing we're going to do is we're going to add some additional materials here, right? And so the two material properties that we're going to test out on this gearbox is going to be stainless steel and cast iron. Okay? So let's go ahead and double click on engineering data. Okay. And just like we normally do, we're going to add a new material. Or I'm sorry, we're going to go from the engineering data sources here. So we're going to click on this button here for the engineering data sources. Okay, we're going to go under general materials, and then we're going to search up two materials here. So we're going to look for gray cast iron. Okay, so gray cast iron, we're going to click the plus there. Okay, and then for stainless steel, we're going to click on the plus sign here as well. Okay. Okay, so let's go ahead and once you've added those two materials, let's go ahead and close out of this engineering data. And then you're going to double click on model to open up ANSYS mechanical. Okay. All right, and we'll give it a couple minutes to do that. Okay, so once you've launched ANSYS Mechanical, you should see your geometry here, right? It's comprised of 3 different parts, and so we have the base, we have the flange, and we have the housing here. Okay. One thing you'll notice right away is that this housing part here is has a blue question mark, right? And then one thing you should hopefully be used to at this point is whenever you see that blue question mark, that basically means that ANSYS is not happy with that, and we need to specify something there. Okay. Okay. And so if you see here, the thing that's missing for that housing geometry here is the thickness of that housing. Right? And so one thing that's interesting about this geometry here is that if you suppress these parts or just hide it for a second, okay, you'll notice that this housing here is actually very thin. In fact, this has already been made into a shell element for you. Okay. And so just like any shell, we need to specify the thickness of that shell. Okay, so for the shell here, what thickness are we using? We're using a thickness of 3 millimeters. And so you may have to change the units here. So I'm going to change this units to this. I set the thickness to 3 millimeters. Okay. Okay, and then from that we are good to go for that. Right? Okay, the next thing we're going to need to do is that because this is a shell surface, it's not actually connected to the base, right? So if you remember from activity 4, whenever you create shell surfaces and beam surfaces, that kind of naturally breaks the natural connections between the parts of your assembly. And so you kind of need to re-add them to the analysis here. Okay. Okay, so just like we did with activity 4, we're going to right click on contacts. We're going to create, or excuse me, insert. We're going to go on manual contact region. And so this is going to create a new contact region between 2 parts. Okay. We're going to click on this. Okay. And we're going to specify the 2 parts here. And so we're going to connect the bottom edge of the housing together with the base right here. Okay. Okay. So for the target here, let's go ahead and apply that to the top surface of this base. Okay. And then for the contact, we're going to select each of the 4 edges that go around this housing. Right? And so you may have to use Control and click to click all of these edges here. Okay. 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 So after you do that, those 2 parts are going to be bonded, and then we are good to go on that part. All right, and so at this point, you should have your geometry loaded. You should be within ANSYS Mechanical. You should have assigned a thickness to the housing so that you have a green check mark here. And you should have added a contact region between the base of the housing and this little base plate that we have at the bottom. Okay. Any questions on this so far? Okay. All right, so next thing we're gonna mesh. And so for the meshing for this part, because we're doing a modal analysis, we actually don't really need anything special. So a modal analysis is actually quite cheap, and it's quite accurate even with the coarse mesh. And so I'm just going to use a default mesh here. So I'm just going to right click on mesh, and then just generate one. It's going to make a mesh for us. Okay, so that looks pretty good. So that's pretty good for our purpose here. Okay. Okay. All right, next we're going to apply some boundary conditions. And so we're going to do something a little bit new today. We haven't done a force like this before, but we're going to make use of something called a bearing. Okay. Okay, so because the way that this part here is used in practice, that you have some shafts that kind of come into these holes right here, and those shafts are going to be pulled, in a direction kind of like this. Okay, and so that's going to apply a force on these inner surfaces here of these holes. Right. Okay. All right, so we're going to apply a force, and so normally when we apply force, we would apply it onto this inner surface just like that. Okay. But a bearing force is something a little bit special. And so whenever you have a rod that's inside a hole like this and it's being pulled across the hole, right? The force is not equally distributed across the entire hole. Right? Let me show you an image just to kind of show you kind of what I mean by that. Right? Okay. And so let's say that you have a hole here and you have a rod that's being pulled up, right? And so because the rod's being pulled upwards, the force that's being applied onto the hole is actually shifted up like this, right? If you were to apply this as like a normal force load with an ANSYS, it would apply the force equally across the entire surface. And so you'd have forces that are coming up like this, okay? Right? But when you have a rod that's inside a bearing like this, and that's being kind of pulled and it's impinging on just one side, having the force equally distributed across the entire surface is not 100% accurate. And so we can apply the load here as a bearing load. Okay. Okay. And so to apply a bearing load, you're going to right click on static structural A5. Okay. You're going to go to insert. And then you're going to go to this image right here called a bearing. Okay. All right. And so the idea with the bearing load is that it's quite similar to a regular force. It's just that how the force is distributed across that surface is going to be different. Okay. And so when you have rods inside holes like this gives you a little bit more of an accurate result than a typical force. Okay. All right. Any questions on that? Okay. All right. So the loading conditions for this is a little bit complicated, and so I would definitely refer to the PDF for that. Okay. And so just for your convenience, I've labeled each of the holes A, B, C, and D. Okay. And then the forces that you're going to apply are going to be given by this table right here, right? So bearing load, so in hole A, we're going to apply a load that has a magnitude of 16,000 newtons in the X direction, a magnitude of 30,000 newtons in the Y direction, and a magnitude of 16,000 newtons in the Z direction, okay? So I'm going to give you guys maybe 5-10 minutes to work on that, and then I'll kind of come check back on you in a little bit. But give the bearing loads a try. So try applying these as bearing loads, and you'll see kind of how that works out. And because you're doing a lot of loads here, don't be afraid to use labels or to rename your loads here.
I got it. Looks great. It's really good.
I can give you the negative cross-sectional area.
That's not good.
Yeah, so I changed my trial one, the positive. Plus ran, and that made a kept it a positive.
Nice. Good. Looks really good.
Yes.
How's everyone doing? Okay. You may run into an issue, or you will run into this issue, that if you're applying your bearing load on, say, surface A right here, it may give you an error saying that you can't apply a bearing load in the axial direction, something. Right? So the reason for that, and so this you'll only get that issue with load A and load D, is that load A and load D have components in the Z direction. Right? And so if you look at the diagram here, the Z direction actually goes down the axis of the hole, right? And so the way the bearing load is defined, you can't apply it, you can't apply a load in the axial direction using a bearing, okay? So that 16,000 newtons of force in the Z direction are actually come from friction. And so you're gonna have to create a separate load for that, right? And so that's gonna be just a typical, just your normal force mode, and apply that in the Z direction on hole A and hole D. Okay. Oh, okay. If you didn't generate an error, then that's okay. No, that's fine. That's kind of nice, actually. So I think probably what it's doing is that it's smart in that it recognizes the axial force, and then it doesn't apply that in the bearing sense. That's good. I was wondering, you guys are really quiet. I'm like, usually I get some questions. But I guess in the new version, I guess it doesn't throw that error. That's good.
They've gotten smarter.
Good. We're paying ANSYS a lot of money, so they better be getting better. Okay, so once you're done applying the loads, you can go ahead and run the simulation. And so just like usual, you can have plots for the total deformation as well as the equivalent stress. Okay. Oops. And so I'm going to go ahead and do that. Yeah. Yes. Yeah. Sorry. So the fixed support's going to be at the bottom of the base. Yeah. Oh yeah. There we go. That's the ANSYS. Typical ANSYS problem.
So do we remove it from the bearing one?
You do, yes. Yeah, so from the bearing ones, you remove the components in the V direction and then just make a new force. Yeah. Yes. So axial load A, this is going to be applied on node A, and it just has a single component in the Z direction of 16,000. I know, I think. All right, how's everyone doing? Was everyone able to get the results? Awesome. Okay. All right. So that's just your standard static structural, right? So this is kind of nothing new here. Okay. So what is going to be new is our modal analysis. Okay. So let me go ahead and close this. Okay. So you want to close mechanical, but you don't want to close workbench, right? So your workbench should still be should still be open. Okay. So what we're going to do is we're going to take our modal analysis here from the toolbox on the left, and then we're going to apply this directly onto our static structural. Okay. All right. So we're going to take modal, you're going to click and drag, and you're going to drop it onto model, just like this. Okay. All right. And so you want to make sure that you drop it here. So what this is going to do is that it's going to inherit the geometry. It's going to inherit the mesh. It's going to inherit the boundary conditions from your static structural that we just completed. Okay. And I know just a couple of you have asked us about the final project. If you wanted to do like a multi-physics type of analysis where you do like maybe structural and thermal, this is basically how you would do it. You basically link the two analyses together just like this. Okay. Okay, so I'm gonna go ahead and release. Okay, and so that's going to create a new analysis system modal here, which we're going to go in and see. Okay. Okay, so let's go ahead and double click on setup here. And so you're going to open up ANSYS Mechanical again, but then now, the modal framework is going to be open instead. Okay, so here is our gearbox again, right? And so our interface here on the left should be mostly the same, except now at the bottom here we have our modal analysis here. Okay. Okay, so you can run this in a couple of different ways, right? And so the first way that you can run it is without any pre-stress. And so, we're going to assume that we're not applying any loads to the structure at all. Okay. So the only thing you have to add here is you have to add a fixed support boundary condition. Okay. Because if you're not going to be inheriting the loads and boundary conditions from your static structural, you still need to fix your gearbox into place. Okay. And so if you're not going to inherit stuff, let's go ahead and add a fixed support here. Okay. We're going to fix it in the exact same place. Right. And you want to make sure you add the fixed support from modal B5, right? Because you already have a fixed support from the static structural A5, but your modal analysis, you want to add your fixed support there. Okay. Okay. All right. So let's go ahead and hit solve. Okay. All right, and so once you hit solve, what you can do is you can click on solution B6 under modal, right? And if you'll notice in the bottom right-hand side of the screen, you have your frequencies. And so these are all of the resonant frequencies of this gearbox. And so our lowest frequency here is 335.44, okay? Our next frequency is 458.22, and so on and so forth, okay? Okay. All right, and so that's modal analysis, basically, ladies and gentlemen. So that's that's basically all there is to it. So now we have your frequencies here, okay? But there is something more interesting we can do. So, you know, the more interesting thing we can do here is we can view the mode shapes, okay? And so to view the mode shapes, you're going to right click, you're going to highlight all of these frequencies here, right? You're going to right click, and then you're going to click on this button here for create mode shape results, okay? Okay, so once you do that, right, you're going to have 6 new plots here under total deformation, right? So let's go ahead and solve it one more time. And then when you click on these total deformation plots, you should see, you know, different deformations. Okay, so total deformation 1, total deformation 2, 3, 4, 5, and 6. Okay. All right. So what are these showing? And in fact, you know, these are actually ones that it's actually kind of fun to see the animation. Right? So remember when we talked about on Tuesday that, you know, when you have resonance occurring in a structure, you know, its resonance deformation is going to depend on the frequency of vibration, right? And so different resonant frequencies are going to have different resonant deformations, okay? And so what each of these deformation plots is showing you here is the shape of the deformation, you know, for those resonant frequencies, okay? So if you look at the deformation plot 2, this one's actually very interesting because it only has deformation on the bottom half here, right? And so if you view it, you know, you can see kind of this surface right here, kind of, you know, almost like kind of vibrating, kind of back and forth, whereas the rest of the structure is mostly staying the same. Okay. And so if you were to force the system at this frequency, the second resonant frequency being 458.22, okay, this is what you would get, right? And you can do the same for 3, okay, right? So 3, you have a little bit of action here up top, but you have kind of this undulating surface here, okay? And 4 and 5 and 6, they're all kind of, you know, more or less the same. This one's interesting, but it looks like it kind of alternates back and forth, right? Okay. But remember what I talked about on Tuesday, that, you know, what you're viewing here is just the mode shapes, okay? Even though this is showing the results as if it were a total deformation, you know, this is not actual deformation here. So we're not actually seeing 57.7 millimeters of deformation here, right? These deformation values are only for reference, right? They're only meant to illustrate the shape. And so, you know, these are not, you know, actual deformation. Because if you remember what we talked about at the end of class on Tuesday, in order to actually get resonance deformations, your input vibrations also have to have a magnitude. Okay. And so be careful when you're viewing these, because these are specifically mode shape results, and they don't actually show the actual deformation. Okay. All right. Any questions on this? Yeah.
Are these frequencies, like each frequency, like on that, like part, is like a frequency that if the part is like exposed to it, like for a long period of time, like it would fail?
Oh yeah, yep. That's the idea, and so that's the idea with these frequencies. And so, you know, the reason you know I chose a gearbox for this is that, you know, oftentimes with gearboxes you have shafts that are kind of running through them, and they're kind of rotating at a particular frequency. And so if the rotation frequency of those shafts matches these frequencies, then that's going to cause resonance, and it's going to cause maybe not for it to fail, but it's definitely going to cause damage to the part that you don't want to have. Yeah. So when you're designing parts like this, where you have kind of rotating shafts, you really want to be cognizant of the resonant frequency. Yeah.
Would you say that like each frequency is like equally as like, I guess like, yeah, equally likely to like make the part fail, or are they just all kind of like have different
They all have different magnitudes, and so typically the smallest resonant frequency is going to cause the biggest vibrations, and so that's usually the one that you have to worry about the most. But the higher ones are still enough for damage as well. But the lowest one is usually the most destructive one. Yep. All right, and so that's so now that's the end of that. Oh, question, yes.
Yeah, like, this mesh, if we're defining the mesh, I think it's like more accurate, like something else.
It would, but the modal analysis is a pretty, low stakes, or not low stakes, it's a pretty, cut and dried analysis, and so if you refine the mesh anymore, like, it's gonna make it more accurate, but it's not gonna make a noticeable difference.
Not like a mesh.
No, yeah, it should be, the modal, the frequency should be converged pretty quickly, even with the coarse mesh. Mhm. All right, any other questions on this activity here? Okay, all right, and so that's the basics of how to do modal analysis. And so if you look at the rest of the activity here, I'm just having you guys just kind of play around with different with the different settings. Okay. Okay, so problem 3 here is a change in the material properties. Okay. And so when you change the material properties, you're going to change the overall stiffness of the entire structure. Okay. And so if you change it, actually we forgot to change the material properties. So the whole thing is actually made of structural steel right now. And so you can experiment with the cast iron and the stainless steel, and you can see how that's going to play an impact on your results. Okay. Problem 4 is geometry. Remember we talked about on Tuesday that geometry is probably the biggest factor that affects the resonant frequencies. And so if you change the geometry in any way, you change the thickness of the base, or excuse me, you change the thickness of the housing, you change the size of the holes, that's going to affect your resonant frequencies. Okay. And problem 5 is kind of a fun one. And so problem 5 is a little bit more in vein of kind of what we've been doing in the class in terms of design, right? And so, after you've done problem 3 and problem 4, where you've seen kind of the effect of the material properties and the geometry, problem 5, I want you to manipulate those things until you get a resonant frequency of a certain value, okay? And so I think the value that I have here is, if you can manipulate the geometry to have a resonant frequency between 190 and 210, that's what this problem is for there, okay? And problem 6 is just summarizing your findings, but you guys aren't turning this in, so you don't have to worry about that. Okay. All right, and so if you're interested in kind of playing around with more modal analysis, you can try these problems. You can also try turning on the pre-stress, and so this pre-stress here, if you want, you can load in the results from static structural. Okay. And if you do that, you have to suppress this fixed support because the static structure already has that fixed support. Okay. And it has to solve 2 systems at the same time. Okay. All right, and so you can see when you add the pre-stress, it actually makes very minuscule changes in this case. So the pre-stress doesn't really do all that much because the loads that we're applying are not super high. Okay. All right, and so you guys can go ahead and play around with it. If you want to use modal analysis for your final project, you can definitely refer to this activity here. That's basically all the content I had planned for today. And so if you have your final project here and you want me to take a look, I can come around and do that. Or if you have questions on modal analysis, I can come around and help you guys with that too. Or you can just head out too. That's fine. Okay, so go ahead and raise your hand. I'll come around and just come around and help anyone that has it.
Oh, that's cool. Your mom behind the area designer I had I used to do all the one I forget what. Remember the line first. Yeah. Well, we may want to suppress the whole. Yeah, but, because it has. So you may want to.
As a backup plan, I would just as a backup plan, where I can go.
That's fine, because it's possible out of the cat, so someone else is hitting that.
Yeah.
That's you, that's engineering. Yeah.
I think that no one I just only know that idea. It's too much. I noticed like this, I did that by myself. So it cannot do that for the project where I am. I'm asking that I'm gonna use half of the chance it is much. Okay, what do you mean?
So if you.
Yeah.
Uh-huh. 73 days, we use that, it's really the same thing.
Yeah, I think, yeah, this, if I'm completely with this way, yeah.
Yeah, you can do that, that's a very common way to do something, because if you have a target of the day.
Yeah.
You can remove it from.
Yeah.
Yeah.
But the thing is, you always do it, even though like, I know if the road is only, like, what happened, why do you have to take all of that? If the road is only here, why to cooperate fine? Only the road is 2,000.
Oh, yeah, so. It's not that, it's not that. You know, I agree. I'll figure it out. I'll figure it out.
On the back side.
Yeah, it's a row.
So now it's going
I think that's,
Yeah.
that's like everything.
That's why it's.
I think you copy it offline. So much.
I know you want to.
But like, sometimes L over D.
Yeah. Anyway, I think it's the process.
So, yeah, I think that, like, I think that that's a line of value. The fact that you're getting the whole, like, majority of the anger is gonna affect them. You've got logos, people, and anything else. Yeah, there is lots of.
I think that's what we got out of
Yeah, I'm gonna try. I can't find.
should send this. I know.
We're pretty good, like, with my product.
It is one.
We did really good on this. Well, it's a lot harder for.
I think that, something is bad.
Under the expected.
I remember I saw you this week. I said, like, go back and add that. Did you add it to those?
I know, appreciate it. Yeah, I think it's looking problem. But if I was sure, if I was like, I can say, if you go to one number, I will use that, this is the way you have to do it. Yeah. Okay, if I did this, I should go, I should get like,
I've never seen
yeah.
I have chance like.
Okay, I would say that. This is why the try and say, don't think about it, even though they say, I would think about it. You should think about it. It should be something rare. It can actually happen. You know, if you have to. No, I mean, like, the doctor said that the information is 0.4 and they got actually 1.2. Yeah, it didn't make a big difference. So the difference I'm not really looking at kind of looking at your logic and how you set up that. So this is the thing I'm simulating, and this is the hand calculation. So I'm looking at the map. So the hand calculation. Okay, one last thing. But I think that we don't use that, use those equations. This is what I'm looking for. I don't use, let's say, spring or, yeah. This is what do you mean by match? So there should be, logic in terms of how you show the hand like the average size of the name, you know, the nine, the apartment that they everything out of it. Yeah. Like, that, so that, yeah, look at that guy before the top, and I didn't do that. We said I did. Yeah, not out of it. Yeah. Actually, I think, I'm gonna put them, okay, one second. So if you're gonna go, what I've been talking to you, if you get it wrongly, I will not. Maybe give it like this. So what are you? We're gonna take your life, we're gonna, you should be five hours. I went to one. And, that was, yeah, that was. We're trying to do a little bit. They have a few moments. The biggest, the one I was. Yes. I don't like the hot fuzz material. And then there was some hybrid back. Yeah. I still only want. And so, and for one of those things, like we use multiple analysis. Perfect. Exactly. Yeah, I think that's very relevant. We want to do it. Okay. Yeah. Five. I don't know. Yeah. I know one year I did do this kind of movie, but so look at this, what I had last time. Perfect. Yeah. And but one of the things is that we don't have the so I already have like everything I've done. Beautiful. Great. Because I already have conditions for ordering breaking, so awesome. So this is great because I already have my. Well, I thought, to be fair, I didn't do it on Sunday. Yeah, because you see the arbitrary data. Yeah, well, I mean, let me try a little bit. I mean, so the minimum for the conversion step, I would like to see maybe at least 4 different meshes. So you can start with something, try as coarse as you can go without it breaking. And you don't have to do the conversion step on every configuration. Yeah, just do it for one. And if you're having trouble getting more elements on it, try it on these computers, because these computers have a little bit of a better version. I think these ones can go up to whereas the one that you download from the website, I think it was up to 64,000. You may have more luck getting the conversion. But it's great. This looks really good. Based on the race car design, I will tell you my so now it looks better. Yeah, I have a lot of nice. That's awesome. Yeah, that's great that you're able to find like a setup on the boundary table. I tried copying it as much as possible. I know for sure what I have done correctly because I from last year's team, we already had on Excel that automated the equations. So I just read the book that you're saying what the equations do and where they come from. Nice. So I know how that works now. So the Excel specifically input the constants and it updates because you already have the equations input. So it saved me a lot of the heavy work on that. So I just read it for nice. Hey, that's
Where I get these versus what I'm watching. It's good. Have it fixed from here, because it's actually the four bearing.
This is nice, this was a challenging geometry, this is a lot of, you know, campers and holes and stuff like that, the fact you got the mesh and what you know, it's pretty impressive.
And even though, even if everything, you know, this is just funny, only knows that in this vision, it's all in the car right now.
Okay, so that's good, so you have validation.
It's just kind of, it's kind of validated.
No,
Good.
I won't do that.
I believe that was always.
Yeah.
By people, it's my only thing was. Everything else is kind of already done on the back of it. I'm gonna put my version.
Yeah.
I already have my different, loading scenario, it's already taken care of.
Is there any significant difference in this,
I don't know.
That's the main thing that I was trying to think of when geometry. So you could treat it as if it were like a hoop, and then do 10 calculations for and then compare that to like the equivalent you guys are getting.
Oh my God.
That would be kind of the first thing that I would think of.
Then they.
Especially because all your money.
When I look at what I want to say,
They're all. Yeah.
Essentially, they were equivalencies. That's why I think the easiest one.
Like, didn't you know, like, I think where I feel like he's one better than all, I always do that, and it's just.
So it's so these students get those, but suppose that we were such, but assuming, you know, proposition is used by practically everybody.
Yes, yeah.
Has to be fine, I would think.
Yeah.
So that's why everything's.
Does the handbook have any equations for like what the factors will be given what these nodes are? For this geometry?
It does have a good for the variance, because you can more or less, I think, if you have similar design, but sometimes the geometry can be different, so I think it would. There's no factor in safety, it depends on the material and geometry things that I think matter the most, but obviously also some of the positions, a lot of the equations have to do with where it's go. How far is this, how is the distance between those two squares is in reference to the wheel and the ground, so how high it is. And so a lot of other things that forces come from the contact of the tire, and to the tire, to the wheel to the upright, and contact with the arms, like, so the connection from the wheel is kind of how the forces go through, but in the book, summarized in the pages and few images, then how the force, the force acting, air bearing, outer bearing, and there's some.
But that's fun. I'm planning to visit like some,
You can try a lunch simulation, maybe you can try just like treat it as if it were, so, you know, you just have a visual. And then apply that as a pressure. Overcame the stress. And then you compare that directly to. So it wouldn't actually be one of your configurations, but it would actually kind of test the geometry in terms of how close you would be. That's one thing that makes sense. A lot of times I get before that. Making an extra configuration. That's just very, very simple. And then use that to compare it. That might be.
What's the other thing else? Anything else as you're going down the list of.
Yeah.
No, this is good, and, you know, I'm really happy to see that. You've kind of been working on it.
No, I guess we'll just.
You know.
Put it out.
Fun, this was kind of-
This is the guy that.
You've done on part.
I'm not in my apartment, I already, I was in Howard was.
I'll take a look at Hancock. I'll let you know. But that's kind of.
That's
kind of the-
I need to go tomorrow.
Yeah.
That's right.
Yep.
I did the visit. Like online.
Yeah. Okay, so we need it. If we do it, is there like a certain software that you prefer, like SolidWorks? No, and you, okay.
So as far as ANSYS is concerned, someone else may be CAD.
Yeah.
Okay. Doesn't matter what.
Well, I look at other things. Yeah. No, I know.
Yeah, well, I don't know.
That's where I was, oh, yeah, you know, when we're talking, only one.
Yeah, I was wondering, yeah, tomorrow, I was like, that time.
And we would have one. Yeah, it's not a big house. Okay. I didn't get out of, you were like, let people out. And I don't think you want to website.
Oh my God.
Right. Right. I don't get good. The on job, we take 40 hours. Yeah. I go wait for hours. I just want my car. Okay. And I want to draw it over. So, I'm doing it. So, we're very like, how did it? Bro, I didn't really.
You didn't really get.
He didn't have to buy himself. What? No. Yeah. No, I got it. Yeah. And then I got yeah, I think I know. It's not gonna be good. Okay, it's very good. So, as I mentioned, graduate, and I got it, I'll go back home. Yeah. Relax, one. But I wouldn't use it. I'm not. I'm gonna take over. I don't like that. I mean, so when you leave it, like, yeah, our country that is usually not in money, and then our something. Yeah. That's funny. That's coming. So, that's fine. If I'm going to Canada, come back, go back to Canada. I mean, if I want to stay, all the reasons that I want to stay. Want to make they have your or you can just ask, even just coming out of school and starting to be I'm not Oh, everyone.
So, yeah, I mean, he's not really negotiating. I mean, does he know? Probably. We know, their job. I don't think we're no longer like. On these, you know, items, it's actually. Yeah. I don't think it. But, you know, yeah. Company never had. Yeah. Everything else that they said, oh, they're talking about. So then, when you. You're gonna be like, yeah, I know. I also don't. First. You can try to find someone. They know that. More like they that's all the great. Yeah. Oh, I don't look at it. Oh, no. Yeah, I got like the great. Yeah, oh, yeah. For all year, I wish I would apply to 60 on the side of the. Okay. Just on the side. Because when you're kind of ramming this thing, you want this part to be able to kind of more. Like, fix support is a good thing, and fix support really is not. Yeah, sometimes I feel like you want to fix the surface, then apply the loss. Yeah, it's good. So that so yeah.
Edgar, Christine, any final questions? Sorry, I was walking around the class a lot. Okay, all right, I will see you guys next week.